Hi, welcome to the next installment, third class 3A1, chapter 5. This is our last module for this chapter. Objective number 6, define and calculate angular displacement, angular velocity, and angular acceleration. So last time we did linear, and there'll be a few comparisons to that. In this, we have similar equations and similar calculations, but we do have a few goofy things that happen in this section. Okay, first thing we have to know is that when we talk about angular motion, we're talking about rotation, and you know, when we talk about circles, we have a bit of language that we use. We have one rotation, we have 360 degrees would be some things that we may use to describe rotation with a circle. When we talk about angular displacement, velocity, and acceleration and do calculations with them, we use generally neither of those things. What we use is a value which is known as a radian. And a radian, if we have a radius of a circle, and we took that distance and we plotted it along the circumference of the circle, what we'd find is that we have, just kind of go on guessing here, we have about 6 of them, 3, 5, and 6, and we're left with not quite one there. And actually what we have is, I don't know, roughly about 6.3 or so worth of radians. We figured out, I guess, that if we talked about a circumference, circumference is equal to pi d. Since a diameter is 2 radians, we had the circumference, or one outside of the circle, would be 2 pi r. So our 2 pi is the number of radians, or radiuses, that would fit on the outside of the circle. Okay. We use radians for our calculations for most of the stuff in this unit. Okay, so a radian is a measure of essentially rotations or degrees, but works out for the math for all of our equations. Okay. One rotation being 2 pi radians. Okay, so what's special about the units for angular motion? We are going to use radians. Okay, and we can use this type of conversion. So one rotation is equal to 2 pi radians, which we also know is equal to 360 degrees. Okay, so if we want to just practice a couple of conversions, so one revolution is 360 degrees is 2 pi radians. How many radians in 248 degrees? Well, we can use our unit conversions. So 248 degrees times 2 pi radians per 360 degrees. Degrees is going to cancel out, leaving radians, and what we would be left with is either 1.38 pi radians. Sometimes we leave the pi in there, or if we want to just use pi as my 3.14, 15928, etc., etc., 4.33 radians. If we want it to convert how many degrees are in 1 radian, so 1 radian times 360 degrees per rotation, which is worth 2 pi radians. Radians is going to cancel out, which leaves me with about 57.3 degrees. Okay. There is nowhere in your supplement where they give you that conversion directly. There is one spot which is at the very end of your supplement in a table known as important data or something like that, which has this table in it. Okay, so buried inside of that is a whole bunch of tables, and it does, that's the only mention of radians, really, what it is, and it tells you it is about 57.3 degrees. So they do tell you 1 radian is about equal to 57.3 degrees. So if all else fails and you forget those conversions, you've got that to fall back on. Inside of our supplement, you have also some other portions which talk about angular motion. Okay, so you have a whole table dedicated to angular motion, and we're going to start sort of talking about some of those things. Okay, first thing that we have is a couple of terms. So if we have here's our circle, and we have say a rope that's hanging off, and it's being wound on or off of that rope, what we have is a conversion between linear motion and angular motion of the rotation of the circle. Okay, and so we use this where we have, first of all, we'll just use our linear displacement, and so what we say is S, which is our linear value that we used in our linear motion, is our distance, is going to be equal to how large the circle is, so what the radius of the circle are, times omega. Okay, and omega, what that is the number of radians that that thing has rotated. Okay, so let's just take a look at a couple of questions relating to some of these equations. So a disk is 50 centimeters in diameter and rotates about the center. What is the angular displacement of the x during 2 rotations? So when we talk about angular displacement, that's theta, and it would be a measure of radians. Okay, so really what we have is our circle, and we've given some geometry information, but all of that is actually really irrelevant. All that we really care about is, in this question, that we've done 2 rotations. So theta, in this case, in radians, is going to be 2 rotations, but that's not the right units for theta. I want it in radians, times 2 pi radians, so I'm just converting here per rotation, is equal to 4 pi radians, or I guess I could have it as 12.57 radians if I work that out for what pi is. Okay, we're going to touch on that question a little later with a second question to go along with it. I'm going to jump to another question here. So I have a spool on a fishing reel, okay, and my fishing reel here, and it's 8 centimeters in diameter, and I guess I'm going to wrap line onto it. Okay, so the line's going to get wrapped onto that reel. And I'm wondering, if I have 15 meters of line to reel in, how many times does this spool have to rotate in order for me to wrap that much line on there. Okay, and I'm going to assume the line is very thin, so as I wind line on there, it doesn't build in diameter and keep increasing like a real spool might do. How many rotations are needed to wrap 15 meters of line onto this reel? Okay, so I'm going to use my linear displacement equation. S is equal to r theta. So S is equal to r theta. S is my distance, so 15 meters, is going to be equal to my radius, so not 8, but half of that, 4 meters, times omega. And omega ends up being 375 is equal to omega. Okay, got to be really careful because when I talk about omega, the units are not rotations, which we use as our normal unit in the real world, but what comes out of that equation is going to be radians. So in order to convert that to rotations, so 375 radians times 1 rotation per 2 pi radians. Radians wipe out, and that gives me 59.7 rotations. Okay. In addition to angular displacement, so we had our displacement, which was theta, and it was in radians. We also have a couple other terms. Okay, we have angular velocity, so how fast is it rotating? Okay, so the symbol for that is omega, a lowercase omega, which kind of looks like a W, a rounded W, and it's really my change of angular displacement per time. Okay. Units for this is going to be radians per second. And just like when we talked about linear velocities, we also had a couple of equations to go along with that, which was like average velocity, or average angular velocity, which was equal to my starting and ending velocities by 2, or else I could figure out average omega as the total, let's call it the total radians that it rotates compared to the total time. So let's take a look at some questions here. So back to our disk from before, the 50 centimeter disk does 2 rotations in 4.6 seconds. What is its angular velocity? So previously what we found was that our theta was 12.57 radians. So omega is equal to the number of radians by time. .57 radians by 4.6 seconds, 2.73 radians per second. Okay. A crankshaft completes 900 full rotations in 1 minute. What is the angular velocity? So omega is equal to the change in displacement compared to time. So what I have is equal to 900 rotations per 1 minute. Problem that I have is that omega wants to be in radians per second, not rotations per minute. So to get it into the right form, I'm going to have to do a bit of converting. So 2 pi radian per rotation times 1 minute per 60 seconds. Rotation will disappear, minutes will disappear, and I'll be left with radians per second. So when I calculate that out, 94.2 radians per second. Okay, so we just went through a case where we had rotations per minute. So how do we convert from angular velocity, so radians per second, to RPM, which is rotations per minute, and that's a very common way for us to speak in real life. So how do we convert from the two? Well, if we just look what we did up here, what we did was we took our RPM times 2 pi divided by 60. So RPM times 2 pi over 60 gives us an answer in rads per second. Okay, and that's a pretty common conversion back and forth. That conversion exists in your supplement. So in your section on angular motion, there is a set of conversions there. So radians per second is equal to 2 pi times RPM divided by 60. Okay, so we got a couple of questions relating to angular velocities and rotations and whatnot. So flywheel is rotating at 250 RPM. What is the angular velocity? So this is just a straight conversion. So 250 RPM times 2 pi over 60 gives me 26.2, and that is in radians per second. Shaft completes 85 turns in 2 seconds. What is the angular velocity? So my angular velocity is equal to 85 rotations per 2 seconds. I like seconds, I don't like rotations, so times 2 pi radians per rotation. That wipes out rotations. And that's equal to 267 radians per second. A winch has an angular velocity of 0.3 radians per second. How long will it take to make 46 rotations? Okay, so I'm going to have to use my omega is, omega is equal to theta upon time, which means if I rearrange that, time is going to be equal to theta upon omega. Angular velocity 0.3 radians per second, and I want 46 rotations. Okay, so 46 rotations. You know what? Maybe I'll do this instead. Skip that. I'm going to do my conversion over here. So 46 rotations times 2 pi radian per rotation. Gives me 289 radians. So T is going to be equal to my displacement, so 289 radians upon omega 0.3 radians per second is going to give me 963.4 seconds. Okay, so manipulation of just my omega equation, just like I might use with velocity is equal to distance by time, and converting gets me a lot of these answers. If we get to more complicated stuff, and I've just redone some of these questions, so it's a little different than your worksheet. Most of it's somewhat the same, but just organized a little differently. So your angular acceleration, we have now an alpha. Okay, so that symbol is alpha, which means acceleration, and it's going to be essentially your change of omega by time. So now that we have a bunch of different things, so we have omegas, we have alphas, we have s's, we have t, sorry, not s's, we have omega. These guys have a parallel, which is to like v and u. We had this guy, which was our a, we had this guy, which was our s, and this was our t. So we have our angular and we have our linear. When we are, or we're approaching questions on our linear, what we had were our linear motion equations. So like v is equal to u plus at, etc. We also have the exact same versions of the equation, but with now angular used. So if we go to our supplement, what we would find is we have this table, which has a whole bunch of stuff in it. Okay, so this is, sorry. So this is the table that is given to you in your supplement. Okay, angular velocity and acceleration. So a couple things that are there. One, it lists off our values. Okay, so displacement, velocity, acceleration. Just note, instead of having a v and a u, they've used omega 1 and omega 2 as initial and final. But what we have is essentially the same linear motion equation. So like v is equal to u plus at. That's the same equation. So we have the same ones that we used before. You've got 1, 2, 3, and 4 linear motion equations. We also have 1, 2, and 3 as our linear to angular conversions. And then you also have down here your radians per second conversion. Okay, so we're going to do a couple questions using the linear motion equation versions here. Okay, so angular motion equations, again, similar to our linear motion equations. Okay, so a flywheel starts from rest and reaches a speed of 200 rotations per minute. What is the average angular velocity of the wheel in radians per second? Okay, so omega average is going to be omega 1 plus omega 2 divided by 2, and that was an equation that we had from the last page. Problem that I have is I have omega 1, which is my initial velocity, I believe. So omega 1 is my initial. Omega 2 is my final. So initial starts out at 0, starts at rest. Final is going to be 200 RPM times 2 pi by 60 is 20.94 rads per second. So my average angular velocity is going to be 0 plus 20.94 over 2, and I would have 10.47 radians per second. Okay. Where I start to use my motion equations, it's going to be here. So the acceleration takes 70 seconds. What is the acceleration, and how many rotations does the wheel make? Okay, so just like I did with my linear motion, I'm going to list my values. This time omega 1, omega 2, t, theta, and alpha. And I'm going to list out what I know. So omega 1 is 0, omega 2 is 20.94, my time is 70 seconds, that's radians per second. I don't know my theta, and I don't know my alpha. So I'm going to go to my angular motion equations and find some equations that are going to work. So I know omega 1, I know omega 2, I know t. So in order to find my theta, I think I'm going to use that equation, which has omega 1, omega 2, and t. And to find my acceleration, I'm going to use that first equation. So I have a omega 2 is equal to omega 1 plus alpha t, and I have a theta is equal to omega 1 plus omega 2 by 2 all times t. So rearranging this guy, omega 2 minus omega 1 upon t is going to be alpha. 20.94 minus 0 on 70 is equal to alpha, and my alpha is 0.299 rad per second. Equal to alpha. Theta is going to be equal to 0 plus 20.94 upon 2 times 70 seconds. Theta is equal to 732.9 radians. My question asked for rotations, so 732.9 radians times 1 rotation per 2 pi radians is equal to 116.6 rotations. Okay, couple of pointers for this just before we wrap up. One, a lot of this just comes down to unit conversions. It's all stuff that you've done with linear motion. It's just really getting a handle on the symbols and what their units are, because they're a little bit foreign from what we do and see and talk about. Let me know if you have any questions. Happy to help you out. Okay, thanks.